Better I never started like actually.
It kind of sucked up your life. I should not admit that I have 10,000 hours in Catholic Exile 1. I should not, probably should not admit that.
We got 6 in Overwatch alone.
I have 650
Sorry?
hours with Linux.
I've not done that yet. Oblivion thoroughly annoys me with its enemies level up with you mechanics that gets in the way of feeling of actual progression. So if you're not into the world exploration and feeling that as progression, it feels like the game actively hates you when you level up.
What game was that?
Oblivion's the world levels up with you mechanics really get in the way of progression. That's as good as Oblivion is, that mechanic really frustrates the numbers nerd in me.
But that's would do anything and release it.
Sorry?
The original title.
Yeah,
And my favorite one is
There's more content involved because of sick.
yeah.
They're just updating the graphics on all of their titles before they release the new one.
past and like completely dominate. What?
I was gonna say, start with that delay,
That is it.
So bad that I forgot.
All right, let's get back into automata and compilers, because we have a lot to cover left this quarter, which is probably not surprising given the pace at which we've been moving. It's been a fast pace, but from what I've seen, people are mostly keeping up and following along. I don't know the extent to which everyone agrees with that statement, but one thing that I have noticed just in general is I think I am seeing too few people in office hours. Those of you who are coming to office hours are doing so with a regularity that I think is great. But my only complaint would be, I don't see enough of you to know who you are individually, how things are going in the class, how can I help you with assignments, with any of this other material. So if you're not someone who's made use of office hours or office hours too much, if I can be helpful, please let me be helpful. I would love to give you nudges and help just talk about how all of this content relates to each other in ways that we don't have a ton of time for in the short period of time that we actually get to meet. But there's a lot of exploration of this material and application of this material we could talk about in ways that would be very useful and helpful for your homework. Yesterday, we talked about CYK. We went over an example of that on the board. The last thing I wanted to talk about with respect to it, since we actually finished the example, which was good, was just iterating again that this is a cubic time algorithm that works for arbitrary grammars. It can work for regardless of the structure of that grammar. It's cubic in complexity. The 3 dimensions were just the length of the string. That's how many n1, 1, 2, 2, 3, 3, how many single character substrings there are. Then the second dimension was needing to parse for substrings of various lengths. So how many substrings are there of length 1? How many different length substrings are there? All substrings of length 1, 2, 3, 4, 5, etc. So that is the second dimension. And then the third dimension for the cubic is the number of possible midpoints that you could split the string into. So as the substrings get longer and longer, the number of possible midpoints grow as well, proportional to the length of that. So you end up with 3 linear time dimensions, which leads to a cubic time complexity algorithm. And it's quite elegant. It works nicely. And I also think that it's a great example of dynamic programming that is one of the most commonly used and least commonly understood algorithmic processes. So I'm hoping that that was informative to go over, because it sounded like only 2 people were truly confident in their dynamic programming skills going into doing it. So hopefully that helped with that. If you want to give me any follow-up on your experience with that, I'd love to hear it in office hours. But are there any questions that I can answer about CYK or about the membership problem before we move on to talking about automata that map to the same level of language as the context-free grammars that we've been talking about? Okay, we're gonna hop into it then. With regular languages, we started talking about the visual way of representing them with deterministic finite automata and non-deterministic finite automata because it was nice to have those visualization tools. Have we noticed that we did not do that here? We started by talking about the grammars, and now we're moving into automata. The reason we're doing that is that while this is a visual representation, it's not a particularly nice visual representation. What do I mean by that? Let's actually dig into how we have to visualize and utilize pushdown automata, because they're not quite as easy to read as regular language automata. So just like with regular languages, multiple different ways to represent the same class of language. With regular languages, we had DFAs, NFAs, regular grammars, and regular expressions. For context-free languages, we have context-free grammars and also pushdown automata. We determined that a regular language didn't have any storage whatsoever. But a context-free language actually has the ability to store things, but it's a limited kind of storage. If you think about maybe how context-free grammars differ from regular grammars, what kind of storage is allowed in a context-free grammar that wasn't allowed in a regular grammar, and what's still missing? What could we do with a context-free grammar and not do with a context-free grammar that allowed for, is there anything in your CS history that maps to this concept? Maybe some kind of structure that maps to the complexity that is allowed for that kind of structure that we've looked at in this grammar type. Anything seem familiar?
Are you talking about like that kind of graph structure you're making?
The kind of, it's more like a data structure.
Yeah.
If you were going to store this data in a particular kind of data structure that would map well to what we can parse and store in a context-free grammar, what structure would map to the power of this language class? It's a good guess. It is a stack. It is exactly a stack. What makes you say that?
You need to be able to store how many items are in the stack.
Yeah, so something like if you can recurse in the middle of something rather than just at the beginning or at the end, we now have this concept of a non-terminal in between terminals or in between non-terminals. If you recurse in the middle, there's something that comes before and something that comes after. So this allows you to now start to store or say that the same number of things come before and after, which is the same thing as a stack, putting something on the stack and taking something off the stack. You can now map somehow to the process of putting something on a stack and the process of taking something off the stack. So that's where we're going to go with regards to this automata, is it's exactly like the regular expression automata, or sorry, just the regular language automata that we studied, except that we are bringing along a stack to each one of these states. And we are allowed, in addition to transitioning between states, to make operations to the stack, either as we transition or staying in the same state. You can loop on the same state, not read input characters, and make changes to the stack. So that's the added power of this automata, but we don't get anything more complicated than a stack. So what does that allow us to do now that we couldn't do before? Can we recognize something like A to the n, B to the n? How would you do that with a stack?
You would have a looping A state, and then you would just keep like the stack of A of B's along with the A.
So
you put
yeah.
an A and then you put a B in the stack.
When you see A's, you would just put stuff on the stack. And then when you see a B, you would map it to an A that you've historically seen. And then if you could just show via some state that you have to see all the A's before you see all the B's, once you see the first B, we can't, when we see an A again, put things on the stack. That would be a failure. But you could then map, do we put things on the stack and then take things off the stack? If the stack is empty when we finish parsing the string, then we know that we're an equal number of A's and B's. And we don't have to have a state that says, I've seen 2 A's and 2 B's. I've seen 3 A's and 3 B's. That was the route that we had to take, drawing this as a as a DFA, and that's why that didn't work, is there was no upper bound for what A and B could be. But if we had a stack with an infinite amount of storage, then we could recognize that. So limit to the amount of memory needed to be able to accept or reject a context-free language? No, we can infinitely recurse in the middle to create this concept of infinite recursion. So we'll take as the example A to the n, B to the n. We know it's not regular. No maximum number of A's that come before the B's. So we would need an infinite amount of memory to be able to store and reject all strings in the language. We agree with that, regardless of, there could be an arbitrary number of A's that come before that B's. And if we place an upper bound on that, then there is some string in the language that we could not accept. We just have to choose a value higher than that maximum. And now there's something in the language that can't be represented. So we need something with a potentially infinite amount of memory to be able to accept or reject an infinite language. So we need an infinite amount of memory. Here is where we're going to start getting theoretical, and this is why automata are used, because the computers that we work with have limits. Servers have limits. Supercomputers have limits with regards to what they can store. So if we are trying to make a large-scale claim in general, we need to think about, what if we had an infinite amount of memory? What could we do and couldn't we do with an infinite amount of memory? And that way, as technology advances, we throw more and more memory together. We can still only do what we can do with a finite amount of memory, but it approaches what we can do with an infinite amount of memory. So let's look at the actual automata type. We're going to label it as a PDA. This does not stand for public displays of affection, as a push down automata. But maybe they're the same thing. If you ever see automata out in the wild acting inappropriately, there's a joke to be made there. So we're going to treat a PDA, a push down automata, like an NFA. So we're going to start not from the DFA's definition, but from the NFA's definition. So in addition to what we can do with an NFA, we're just keeping track of the state of a stack at each state as well. So a state defines where we are in terms of an input character, whether it's state as final or non-final, all of that stays the same. We just now need to further define the stack alphabet and something that represents the bottom of stack character. Yeah.
Is it each state has a stack, or is it a global stack?
There's a global stack. So if we're looking at the actual official definition from the book, it looks very much like the regular DFA, except that now we just define the stack alphabet and a new transition function that now incorporates that we can make changes to the stack in addition to changes between states on certain input characters. So we have the input file, we have the control unit, which is the states and transitions, and then we have this stack. So we're going to make changes to this stack as we transition as well. So now to define this state machine, we also need to define transitions with regards to what changes do we make to the stack. Questions on any of this concept? Yeah.
What's the third character in the formula there?
I wanna say that's that row.
It's a capital gamma.
Yeah, is it capital gamma? I actually don't know off the top of my head. I've been asked that question before. I looked it up, I had an answer, and I don't remember anymore.
Which one are you talking about?
It is a capital gamma. Excellent.
Nice.
You can tell I'm not a true math professor because I don't know all of the Greek letters off the top of my head.
Is there a deterministic pushdown acceptor?
There is. We'll talk about that later. And the reason we don't introduce it is because it actually is a different language class. In regular languages, DFAs and NFAs can be mapped to each other. They represented the same language. In context-free languages, that's not the case. So what maps to the grammar type that we have seen is a non-deterministic pushdown automata and not a deterministic pushdown automata. Yeah, that's a great question, though. We will talk about it in more depth when we get there. So one change to this is the domain and range of the transition function. Instead of just transitioning from one state to another state on an input character, we're going to do that as long as there is a particular character on the stack as well. So we have full freedom now of being able to say make no change to the stack. This transition is only legal if the top character of the stack is a particular character. So that becomes another dimension that we have in terms of a control of the construction of this automata, is we can allow or disallow particular transitions based on what is currently on the stack. Allow for certain transitions only if the stack is empty. Allow for certain transitions only if a particular character is on the top of the stack, but we cannot dig down the stack to try to find. It's the third thing from the bottom, this particular character. So we also need to make a change to the stack on every transition, although that change can be a no operation, a lambda transition for the stack. So that transition can be a push or a pop or a no op. If the stack is actually empty, we can't do anything. So we need to, there's the concept of a bottom of stack character, which is the equivalent in code to just calling is empty. But we are going to have a particular bottom of stack character. So that if we peek at the stack and see the bottom of stack character, then we know that the stack is empty. That's the equivalent of calling is empty in code for our purposes. We also are forcing the range of this to be finite. We can't have an infinite possible transition space. So the number of states and the number of transitions must be finite, just like it was in a DFA or NFA. We got a finite number of states. This will have a finite number of states. And this also means that what the possible transitions are is also finite, because we have an input alphabet that is finite, just like before. We have a finite stack alphabet. This means that the total number of transitions from states will be finite if you have a finite number of states. Yeah.
Are the transitions going to look like, on an A, take the A from the input and also change the stack at the same time? And then you
Yes.
have two of those.
Yep. It's going to be much more complicated in terms of we need much more information now. Yeah, it's going to be the input is a triple that has, if you're in a state, see an input character and have something on the stack, then transition to some new state, make a change to the stack.
But because it's like based on the NFA, we can have multiple of those.
Correct.
couples.
Yep. Since it's an NFA, everything from non-determinism applies to a non-deterministic pushdown automata as well. So this tells us, though, that we're in a finite realm. We can, the memory that's used for the definition of this is finite. That's really all that means. We can construct this machine with a finite amount of memory, even though the stack that comes with it is infinite. So here is what a transition looks like for an NPDA. This says if we're in state Q1, we read an A and there is a B, we're going to pop the B from the top of the stack. Then we could transition to Q2, pushing a C and a D onto the stack. Or we could transition to Q3 and no op the stack. So we already popped the B. Let me actually draw this out, because this is one of the points of confusion for this is we must guarantee this pop character. If you really want to do a no op, you must pop the B and then push it back on. And that would be the equivalent of a no op. But there's no peak. The peak is going to be via a pop. So this says, here's the starting state. Here's the character we're reading in the input alphabet. This is the character that must be on the top of the stack. If all of that is true, pop this character from the stack, transition to one of these places, and push whatever is this onto the stack. So this would say push a C and then push a D.
What if you have to pop the character off to make the transition, then you no longer make the requirements for putting it back on?
Then it's gone. So yeah, this gets rid of the B. So in order for that B to be back on the stack as a peak, then you have to push it back when you reach there.
Can you draw that up?
Yeah, we're gonna have some examples of this, but yeah, it's so let's say we're in a state, this state is called one. This says that in the input character, we are reading this A, so we're moving past this A. Who knows how we got here? Who knows what comes after, but we were on that A. So there's an A in the input string. On our stack, there's a bunch of unknown stuff, and on the top of that stack is a B. So this transition going from Q1 to Q2 is on an A, but it also is on a B on the stack. So instead of being able to show this, you now kind of have to put it as a tuple. It's something that says on an A on stack on a B. So a lot of these transitions are defined and look like this because it is such a pain to show on an actual diagram. And we'll see how NPDAs actually have surprisingly few states. And a lot of the time, we're actually looping back to the same state, just making changes to the stack as we do it. So you get states with 10 transitions back to itself. And it looks really gross. Self loop, 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 self loop. Is that particularly readable? Really hard to get a sense of what is this actually doing. So yeah, it's the concept of just, we're gonna pop this B when we make this change. And then this would say, we're going to push a C and a D when we get there, when we reach this. So we pop the B when we leave. When we enter Q2, we're gonna push a C and a D. There's another one on the same two characters that would go to Q3, but we push nothing back on the stack. Yeah.
You can't push strings, so which one goes first onto the stack? The C go first?
Does the C go first or the D go first? That's a great question. That depends on exactly how you're reading so the book. Let's see, does that state here? The string CD replaces B on top of the stack. So this is still thinking that you can make a string of multiple characters for some reason. If we're working on something that is separate than that, I will assume. Yeah, done symbol by symbol, starting at the right end of the string. So yeah, this would say that we're gonna push the D first and then the C. So from right to left. You should be able to read this straight down from so you would see C and D replacing that B on that. Push the D first, then the C ends up on top. Questions? One of these days, this is going to cross my desk. The day is not today. All right, so here are some transitions. Kind of gross. I don't know if that's particularly visible. I can zoom in on it. There we go. This says the final state is Q3, but go ahead and think about what does this do? Can you, from these transitions, just the transition list, determine what this state machine does? So it's operating in binary. But the binary is the stack. Note that the input alphabet is A and B, but the stack is binary. So what over A and B does this do when you can look at the stack? This is saying that from state Q0, when we read an A and a 0 is on the stack, then we can move to state Q1, push a 0 and then a 1, or go to Q3 and remove the 0. This says that the bottom of stack character is a 0. The point of this exercise is that it's really hard to do. I don't have an expectation that this is particularly readable. And frequently we want to actually draw it out as a transition graph, just like we did before. So just like in an NFA, if there are no transitions, that is an instant rejection. And this is good because trying to figure out every possible set of stack. Basically, you have pairs between on every input symbol, on every possible top of stack character, we would need to define some transition, and that would get really gross. So there's no reason to do that. It will just be way too many useless transitions that would do that. So if we want to analyze this and figure out what it's doing, the first place that you might start is when an A is read, we push a 1 onto the stack. Whatever was on top of the stack, doesn't matter, we're gonna put a 1 on top of that. It removes a 1 from the stack whenever a B is read. Do we see how that's present in these? We see an A, if there was a 1 on the stack, we're gonna add a 1. Now there are 2 1s to replace that 1 1, where this got popped. So you push 1 to replace it and then an additional 1 on top of it. If you read an A here and there was a 0 on top of the stack, you would either add a 1 on top of it or be able to transition and remove the 0 to an accepting state. So we can transition from Q1 to Q2 after the last A is read. So this Q1 to Q2 can just transition removing a 1, or Q1 to Q2, that's the only way you get from Q1 to Q2. So we get a transition graph that looks kind of like this. So what you write here is not just a single symbol. You write 3 symbols on your transition graph for each edge. On an A, if the top of stack character is a 0, pop the 0 and replace it with 1 0. So you're keeping the 0, but you're adding a 1. And that's how to read that transition. On an A, if the top of stack character is a 1, pop it and replace it with 1 1. 1 that replaces it and 1 additional 1 on top. If we're in Q1, input symbol is a B, and there's a 1 on top of the stack, then we just pop the 1. Replace that 1 with nothing. As a transition graph, is it a little easier to see what this is doing? What's it doing? We can go directly from the start to acceptance if we see an A. Or we can just lambda transition there, getting rid of that bottom of stack character. That says that we accept the empty string. So the empty string is accepted. If we see an A, we can immediately accept. Otherwise, we see an A, we're going to start counting those A's with a number of 1s on the stack. As soon as we see those A's, we're just going to add more and more and more of them until we transition to seeing B's. Once we see our first B, we're no longer allowed to see A's. We're going to replace since now all there are a number of 1s on top of the stack equal to the number of A's that we saw. Once we see our first B, we're going to start removing those 1s. And we can kind of lambda transition. We see that bottom of stack character as 0. We can lambda transition, making a no up on the stack, reading no characters in the input to teleport to a final solution, but only if we've read a number of B's equivalent to the number of A's that we saw before we transitioned and saw the first B. So this represents A to the N, B to the N.
So NPAs can't prove regularity. Right?
Correct. Yeah, this is a larger class of language than regular languages. In fact, we proved that this language was not regular.
Yes. So,
So now we have a way to represent it. We just have to use a state machine with a stack instead of a state machine with no memory.
what does this say about A to the N, B to the N though?
It says that it is context free.
That-
So-
that's a valid way to prove it is to draw.
Yep, NPDA or a context free grammar are as a way to show that a language is context free.
Why does it accept A, like just by itself with no B's, if it's A to N, B, yeah?
Yeah, so I guess this would remove it from the stack and you have to have that bottom of stack. It has to be empty. That's a good question. I have no idea why that's there. It's A to the N, B to the N, union A.
It's fine. Okay, cool.
Yeah,
Could you possibly walk through an example of like A to the two, B to the two, and like manipulating the
yeah,
stack?
yeah. So we want to see A, B, B. We have some stack that we're keeping track of for the memory. We start in Q0 and we start with a 0 on the stack as the bottom of stack character. This tells us that the stack is empty. If we try to pop this and get that 0, that is what tells us empty stack instead of having to call it as empty. So this is the starting location. We're going to be looking at this A to start with. So we say there are multiple transitions out of here. On an A, reading a 0. So we're on an A, there's a 0 on top of the stack. We can move in either of these directions. If one of them leads to acceptance, then we will accept. We have to be done reading the string though, with an empty stack. The bottom of stack character has to be there. We can't just, it's no longer enough to be in a final state by itself. We now have to be in a final state with an empty stack. All right, so let's go the actual way. So we're gonna A0, 1, 0. This says that replace the 0 with a 1, 0. So we're going to put the 1 on top of the 0. And now we are in Q1, having read past this A. From here, there are two edges. If the input character is an A and there's a 1 on top of the stack, this is an A, there's a 1 on top of the stack, we can make this transition and replace this 1 with a 1, 1 and move past the A. We're still in Q1. On a B, if there's a 1 on top of the stack, which on a B, there is a 1 on top of the stack, we can transition from Q1 to Q2. But we replace that one that's on top of the stack with nothing. So it's the equivalent of a pop. We're in Q2. We moved past this B. We can read this B, and if there's a 1 on top of the stack, we can get rid of the 1 on top of the stack and parse the B. Move past the B. So now we're at the end of the string. We can make no change to the input string. If there's a 0 on top of the stack, get rid of that 0. So now we're in Q3. We're at the end of the input string, and we have an empty stack, including getting rid of that bottom of stack character. That's no longer there. This is an actual empty stack. And this means that we can accept. If you're in a final state at the end of the string and have an empty stack, then you can accept. So this entire process, accept this string and say that it is in the language that this NPDA accepts. Questions about that process?
Just started with the 0 because that's what the first A started with.
It's what was defined to be the bottom of stack character.
Oh, let's see.
Yeah,
Will there ever be a time where it's not defined as something?
yeah, you would need to know as part of the definition of an NPDA what that bottom of stack character is. Usually we will use lowercase z to represent the bottom of stack character just because it is easy. In this case, it's a 0. I think in every other example I use for the rest of the quarter, it's always lowercase c.
So just to kind of cement this, so when you're doing, like on the first A that we did where it was the A0, 1, 0.
Yeah,
So you're just putting the first digit. Why don't you put 1 and 0?
it's because we're popping this 0. So pop the 0, push a 0 as the equivalent of a NOA.
Oh, okay.
Yeah, so the second thing gets popped. And then whatever is here gets pushed from right to left. So for simplicity of not erasing something and then writing it again, I just assumed that this was a no-op and then wrote the 1 on top. Yeah,
Can we start the stack with multiple variables in it, or does it have to start with?
it has to be a single character.
Oh,
If you needed to put multiple things on, then you could define those transitions for that initial
so you
state.
just hard code it.
Yeah. Okay, how are we doing? Make sense so far? Bored out of your mind yet? A little bit?
That makes sense.
So let's talk about instantaneous descriptions. This is something that we did for, we need to introduce this concept because transition graphs are great for DFAs and NFAs, but they're not quite as useful for pushdown automata. So we're gonna define a new notation that we can use to describe something. So we're gonna use a triple. We're gonna call this triple Q, W, and U. We're gonna say Q is the state of the control unit, Q0, Q1, Q2. W is just the portion of the string we have not read yet. And then U is the stack contents, the entirety of what the stack is. We can now state that a transition from one state to another state in an NPDA can be described as just moving from one triple to another triple. So let's give you an example of that. Let's see if we can construct an NPDA for a language. So the language is going to be the number of A's is equal to the number of B's. We do not have to have them in a particular order now. A to the n, B to the n was a subset of this language where all the A's had to come before all the B's. But now that's not the case. We want to accept all strings that have an equal number of A's and B's, regardless of the order that they appear. To give you a push in the right direction, think about solving this with a stack. How could you use a stack to be able to represent an equal number of zeros and ones? How is that different from the problem we just looked at?
You would need one. You would need a different character for A and B, wouldn't you?
That's a very good insight.
Because if you can't go negative, the same way we did it last time, you would have to account for if there's more B's than
Yeah.
A's.
How are we gonna do that? Yeah. Just like with a lot of coding concepts, I think it's useful to spend a little bit of time designing a solution in your head, coming up with how are these related to each other? What would I do algorithmically to solve this? And then start to write out the automata for it. It's not quite as useful to take an iterative process to this. Because you're gonna find that you make assumptions, like there are always more A's than B's. That's a much easier solution than having to consider that there may be at particular points in the string more B's than A's or more A's than B's. And that is a distinct idea. However, is it a distinct state?
Can you make this initial state with no input be the final state in this?
You could. If you do that, then you expect the stack to be empty. So there should be a transition to itself to remove that bottom of stack
You only
character.
have one final statement there.
You can have any number of final states, just like before. But I will argue that we only need one final state for this. How many states do we think are in this solution?
Four.
I think 3.
I think we can even do it in 2. Yeah,
Yeah, 'cause you would have your starting state, which the stack is empty. And then you have a state where there's something in the stack. and then calls back to that one where you're either adding an A or a B, and either one is A and B is 0. And we want the stack to be empty, so every time we see an A, we add a 1, every time we see a B, we add a 0, and then if we would need some way to like, we need to pop those off, so I'm not sure.
Yeah, we need a way to count them.
Wouldn't it have to be 0, 1, and 2, because 0 is the, or if Z is the stack character, we could use 0.
Yeah, we can assume that the stack starts with that bottom of stack character already counted. Yeah, we don't need to add the bottom of stack character as part of,
The stack language.
Are we able to do lambda as a pop option?
yes, well, yeah, so lambda now can appear in two places. One, to avoid reading a symbol in the input, but also to do a pop without an associated push on the stack. If we do need to add that bottom of stack character, then it is a three-state solution. Yeah, what do you have?
So I have Q1 transition, or sorry, Q0 transitions to Q1 on an A and a B, and then you have to pop the 0 or 1 and whatever. And then put back either a 1 for A or a 0 for B and the starting character. So you can only transition out of Q1 by consuming the end character. And you
Yes.
just put it back on. And then you loop back on Q1 for every possible state, just keeping track of zeros for B and 1s for A. The only way you get back to the accepting Q0
How are you keeping track of the zeros and ones?
with the stack. I'm just like,
So let's say an A represents a 0 and a B represents a 1.
hmm,
If you've seen an A, so there's a 0 on the stack, and then you see a B, what happens?
It only works if the strings of palindrome. Because you have to take them off in the same order as you put them on.
Yeah, we need something a little bit more clever. So I'm gonna draw a solution to this, yeah,
So if the top of the stack isn't the thing that is the next character, then we add that character. But, or if it's the opposite character, then we pop it.
Yes,
But
that's
if
the
it's the
solution.
thing, then we push it.
That's the solution. Yes. So we're going to assume that we start with a Q0 that is an initial state. We need to get that bottom of stack character on there. We're going to have a transition just to do that. So we're going to say that the triple for that is if the basically on a nothing, we're going to pop a nothing from the stack, and we're going to push the bottom of stack character. So a lambda lambda z is the way to say making no change to the string, popping nothing off the stack, push the bottom of stack character onto the stack. And that transitions you to this state that I'm going to draw that is Q1. And I make it this size for a reason. So we have a lot to do in this state. Thinking about our stack, now to be in Q1, we need to have that bottom of stack character on there, but now we want to start to read from the input string, the A's and the B's. So what do we want to do on A if we see a bottom of stack character? So this is going to be one transition from Q1 to itself. It says with reading an A from the input, if there is a bottom of stack character, what do we want to do? Push. We want either a 0 or a 1, I think, to make this to distinguish.
Option 0.
Yeah, we'll push a 0. So we need to both have that bottom of stack character there, and we want a 0 on top of it. So pop the Z, push 0Z. So on an A, we can now add a 0 on top of that. Great. What happens if we see a 1 with a bottom of stack, sorry, see a B with a bottom of stack character?
Same thing with the B and a 1.
On a B, Z, we want 1Z. in a way that can now add a 1 on top of that if we see a B. So we've handled now the 2 cases of seeing a bottom of stack character aside from the one that's going to say, when we see the bottom of stack character, we can now transition to a final state. Let's actually draw that out. So we want to read nothing from the input. We want to see the bottom of stack character. And just putting the bottom of stack character directly back on it, we can do that. Or if you want to accept with absolutely nothing, you can remove that bottom of stack character and get to a final state that is Q2.
You mentioned
Could you
the
make
stack.
Q0 final
Yeah, we should.
and go back to Q0?
What's nice is you can just hop here like that. So yeah, you could also make Q0 final to handle that. But we need the ability now to be able to say, we've read some A's, we've read some B's, we end up with an empty stack after we've done that. So now we can transition here. If there are no characters in the string to read, it is the empty string. There's nothing that says we can't just read nothing, put the Z on the stack, read nothing, pop the Z off the stack, accept. So that's the way that we would accept the empty string. 2 equivalents of lambda transitions. Teleport to the solution.
Do you need to have different loops back themselves for each one of these, or if you?
No, you can multi-edge it. It's just that you can become, it can become, yeah, a very long list. So I like to at least have different transitions for different ones. If anything, I would combine these 2 as this is what handles the bottom of stack character being in Z. Otherwise, doesn't matter. But now let's take a look at what happens if we have either 0s or 1s on the stack. So let's assume there's a 0 on the stack now. So what happens when we read an A and there's a 0 on the stack? So in other words, there's an A in the string, and this 0 represents that we've seen more A's than B's so far. That's what this idea is going to be. We want to push 0, 0, because now this isn't the bottom of stack character anymore. We want to push an extra 0 to say, if we'd seen 1 more A than B, now we've seen 2 more A's than B's. If we'd seen 5 more A's than B's, we've now seen 6 more A's than B's. Yeah, because we had to pop that 0 to peek at it. So I'll pop a 0, push that 0 back on, push an extra 0. Similarly, if we read a B and a 1 is on the stack, this is kind of a mirror of this one. A B with a 1 on the stack, we're going to add another 1. This is the state that would say, we've seen more B's than A's so far. We see another B, we've seen 1 more B than A than we had before. The final transitions will be, if we see an A and there's a 1 on the stack, what does that mean?
More B's and A's.
We've seen more B's than A's, but we see an A. What does that mean? It means we've seen 1 fewer B's than A's than we had before. So we should do what?
Push nothing.
Push them.
Nothing. We pop to the 1 and that's okay. There's no additional push from that point. And it's exactly the same with a B, just with the opposite character. We see a B, there's a 0 on the stack. We want to remove that 0 in a way that says we've seen 1 fewer A's than B's when we read a B. So this is complete. If we wanted to read a string like A, B, B, and say, are there the same number of A's and B's? They don't come in the same order. We would transition here, putting the Z on the stack. Read the A, since there's a Z on top of the stack, it's this transition that says, keep that Z there and push a 0. We then move to the second character. It's going to be this transition this time. We read an A, there's a 0 on top of the stack. So we're going to keep that 0 there and add another one, saying we've seen 2 more A's than B's so far in the string. Moving to the next character. We are now here, there's a 0 on top of the stack, but we're reading a B. So we're going to make this transition that says, take one of those zeros off the stack. So we're going to take one off, and now analyzing this, we can see that there's been one more A than B that we've seen so far. We've seen 2 A's and 1 B, but we don't actually know exactly how many. We're just keeping track of the comparison of the amounts. From this A to the 0, so we're back here again, adding another 0 back onto the stack. There's no way to distinguish when we were here versus when we were here. Because we're not actually counting them. It's just the state of, there are now 2 more A's than B's, just 3 and 1 instead of 2 and 0. Then we will read 2 consecutive B's that get rid of this 0 and this 0 in 2 transitions that will lead us to the end of string. So we can now access this. We remove the Z from the stack, transition to Q2, since we're at the end of the string with an empty stack and in a final state we can accept. We could have teleported at some other point, maybe if this was AABB, AB, if we did that, at this point, the stack would have been empty. AABB would have been, just had the bottom stack character on it. We could have transitioned here, but what keeps us from accepting at that point is we're not at the end of the input string. So in order to accept, all of those conditions have to be met. That stack is empty, end of the input string, and in a final state. All right, that is the day. Any questions that I can answer before you head out?
You mentioned you could use some few states.
It would only be if we had already assumed the bottom of that character was on it. And there are differing opinions on exactly how much you need to put that in your state machine. Do you just assume that the bottom of stack character is already there, or do you actually have to manually put it there? So for what, my opinion on it? This is complete, and the other is more of a shortcut. And sometimes I like to be able to accept something with the bottom of stack character on it, so you don't have to transition, make a forced transition to it. The end state here is now if the bottom of stack character is on the stack. So as long as you're clear about what the assumptions that you're making, I'm fine with it. But I think the default should be that we should put the bottom of stack character on, and we should take the bottom of stack character off. If you're going to skip those other steps, then state it somewhere in a homework problem saying, I'm assuming that we're starting with the bottom of stack character already being on.
Just save some gravity.
Yeah, it's just an extra state. All right, I have office hours starting right now for anyone who has questions on homework, any of this material, anything else about the class, anything else about the degree, a future career. Let me know how I can be helpful.